When you rub a glass rod with a piece of silk, the two materials cling together. It appears to be a simple macroscopic physical interaction. But if we drop down to the scale of the atoms, that smooth friction gives way to a rigid, highly structured lattice in constant motion. To understand exactly how matter behaves at scale, we have to establish the bedrock classical mechanics of electrostatics, starting entirely from fundamental axioms. We will define the discrete rules that govern atomic behavior, calculate spatial interactions across empty space using Coulomb's law, and mathematically prove the dominance of electrostatic forces over gravity. The mathematical framework for these spatial interactions was first developed by Charles Augustin de Coulomb. He quantified forces that were previously invisible to the naked eye. His exact quantification did not rely on pure theory. He proved the mechanics using highly sensitive torsion balance instrumentation, allowing him to measure infinitesimal repulsive and attractive forces with strict precision. These mechanics of electrostatics form the physical bedrock that dictates how matter interacts in the universe. We start by examining triboelectric charging, the friction generated by rubbing that neutral glass rod against the neutral silk cloth. This process operates strictly on the conservation of charge. Applying friction to a material never creates or destroys a charge. It is entirely a zero-sum transfer of pre-existing electrons. This schematic visualizes the rod and cloth at the moment of contact. The physical friction physically strips electrons, denoted as E, from the glass lattice and forces them to migrate over to the silk. The glass loses electrons and becomes positively charged. The silk gains those exact electrons and becomes negatively charged. Throughout the entire transfer, the net charge of this closed system remains locked at absolute zero. Every macroscopic electrostatic charge, regardless of its mass, is simply an accounting imbalance of fundamental subatomic particles. Because charge is tied to physical electrons, it obeys the axiom of quantization. Charge only exists in discrete, indivisible packets, with an elementary magnitude of 1.6 times 10 to the power of negative 19 coulombs. We express this with the formula Q equals NE. The total charge, Q, must be an exact integer, n, multiplied by the elementary charge, E. This 2D graph plots total charge on the y-axis against the number of electrons on the x-axis. Notice the strict step function. A charge of 2e or negative 3e plots perfectly. A fractional charge like 1.5e is mathematically and physically impossible. There is no half electron. For ordinary macroscopic objects, the total number of electrons transferred is so massive and the elementary charge so infinitesimal that these millions of individual steps blur together. The continuous flow of static electricity we observe is an illusion of scale, masking a strictly quantized physical reality. To map the spatial mechanics of these discrete packets, we use this 1D vector diagram. It plots a physical system of two positively charged spheres, Q1 at 2 times 10 to the negative 7 coulombs and Q2 at 3 times 10 to the negative 7 coulombs, separated by a defined vacuum gap of 0.30 meters. The interaction across that gap is governed by Coulomb's law. Force equals the electrostatic constant K times the product of the charges divided by the distance squared. The constant K scales the interaction for empty space, locked at 9 times 10 to the 9th. Substituting our known values into the equation, we place the charges and the constant in the numerator and the 0.30 meter spatial separation, squared, in the denominator. Multiplying the scientific notation isolates 10 to the negative 14th in the numerator. Dividing by 0.09 yields a final force of 6 times 10 to the negative 3rd newtons. Because both charges are positive, the vectors point outward, driving the spheres apart. Electrostatic interaction scales directly with the product of the charge magnitudes, and it is exponentially weakened by spatial separation. Now we reverse the geometry. This new vector diagram establishes a system with a known attractive force of 0.2 newtons, acting between highly asymmetrical charges, a positive 0.4 microcoulombs and a negative 0.8 microcoulombs. To find the separation gap, we rearrange Coulomb's formula algebraically. We multiply both sides by distance squared and divide by the known force, isolating r squared on the left. Plugging in the charges, multiplying, and resolving the final square root calculation yields a precise physical separation of exactly 0.12 meters. Consider the force acting on the second sphere due to the first. Given that the second sphere carries twice the charge magnitude of its partner, it may appear that the resulting force it experiences should be similarly doubled. However, according to Newton's third law, the force generated is mutual. Even with this charge asymmetry, the force on the second sphere remains exactly 0.2 newtons, oriented in the opposite direction. Electrostatic force dictates a symmetrical interaction. An extreme asymmetry in charge magnitude never breaks the mechanical symmetry of the resulting force vectors. We can subject this electrostatic model to an ultimate physical test by comparing its raw power directly against gravitational mass. This sets up the benchmark ratio. We divide the Coulomb constants for an electron-proton bond by their gravitational constants. To prove we can compare them, we expand into base SI units and cancel newtons, meters squared, coulomb squared, and kilogram squared. The units cancel out entirely. The result is a pure, dimensionless ratio, giving us the mathematical authority to directly compare the magnitude of the two fundamental forces. The final numerical value of this comparison resolves to approximately 2.3 times 10 to the 39th power. This 39 order of magnitude disparity confirms that at the atomic scale, the influence of gravity is mathematically negligible. At this level of interaction, the electrostatic force is the dominant mechanism holding the atom together.